Okay, good afternoon, everyone. I'm Duo. I'm a first-year PhD student in the computer laboratory of University of Cambridge. And today I'm going to be presenting to you about this work, which I've done with one of the master students in our research group. And it's titled Multi-Modal Biomedical Image Segmentation by Neural Network Fusion. So first, let me start. Ooh, doesn't work. Okay. So first, let me start by introducing to you what is actually multimodal biomedical image. So in modern medical diagnosis, actually, the doctors and the radiologists, you actually use more than one type of medical imaging techniques to help you diagnose and treat the diseases. So for example, you can have the computed tomography, and we can have the magnetic resonance imaging, and we can also have what's called the positron emission tomography. So all the three different image modalities are shown below in the order. And so for many diseases, for example, for cancer and for brain tumor, actually, what the radiologists found is that if we use more than one image modality, it actually helps us to improve the diagnosis and the treatment. So for multimodal image segmentation, so for the images that can be closely registered, that means you can put the image aligned and for example, like the head image, because head is relatively a rigid body, so you can register the image of head in a very relatively easy way by just a rigid transformation. So you can register them in a close position, and you can stack them together so that you make them into an image, and each modality corresponds to one channel in the image. But it is actually very difficult to do so for many other parts of the human body area, because there's a lot of soft tissues in many parts of human body, for example, in the abdominal area. So the soft tissues deform very easily between scans to scans, and it's actually, there's not a working co-registration methods to register all the soft tissues in the abdominal area. As you can see from the diagram on the right, so the soft tissues, they are all in different places. They cannot be registered in a simple way. But is this the end of the day? No. We can still have some way to actually take advantage of the multimodality data, even though they cannot be co-registered. So before that, let me first give you some idea about the architecture, which is a convolutional neural network architecture that we have been exploiting. So I think most of you are very familiar with the CNN already. So basically, in a CNN, we know that for the lower level, the layers will extract lower level of image information, such as the edges and the blobs in the image. And gradually to the upper layers, it extract more higher level features. For example, maybe in the second layer, for the car, it will extract some part of the car features, such as the wheels, the car windows. And then in the more higher layers, it extracts more higher level concept, for example, the concept of the whole car. So what we are trying to exploit is that, so let's say we have different image modality, but we're looking at the same organ, for example, your liver or a tumor. So the higher level feature representation of that tumor should be relatively independent from the image modality that you are using. So if you view let's say a tumor in CT or MR image, it shouldn't affect that you actually still see that this is a tumor. So let me first introduce you maybe to one of the data sets we are using. So for this project, we are targeting one of the diseases called abdominal aortic aneurysm. So aneurysm is a disease that causes your aorta. So aorta is the main artery of human body, and it causes part of your aorta to have a balloon-like bulge. And this bulge is actually very deadly, because once it ruptures, it will cause 40% of the death rate. And so in our data set, we have a CT and MR abdominal scans of 21 anonymous patients. And so below is an illustration of what is actually a segmentation task. So we have the image patches extracted in the axial plane, that means the horizontal plane. And so the the task is actually to segment the image into different classes. So on the above, you can see this is a CT image. So we want to segment them into 5 different classes. And in the below is the MR image, which will be segmented into 4 different classes. So the CT image, so these 2 different image modality has their advantages, disadvantages. So for CT image is able to show the blood and the calcium deposit much more clearer than the MR image. But MR image is able to show the boundaries between soft tissues much more clearer than CT image. So each has this advantage and disadvantage. So that's why we want to combine them together. And so for the neural network for segmentation, it's actually, we are using a very popular architecture, which is an encoder-decoder architecture. So the encoder, so this architecture has 2 parts. The first part is the encoder, which encodes the a raw image into a higher level feature representation. And we also have a decoder part, which decodes the higher level feature representation into what we call a segmentation map, which is the map you see on the right. And we also added 6 skip connections, which pass the lower layers in the encoder to lower layers in decoder, which has been shown to improve spatial accuracy in segmentation. And a naive way to train, so we have the image data set has the CT modality and MR modality. So a naive way to use this data set is we train one model to segment the CT image, and we train another model to segment the MR image. But this actually doesn't take full use of the information contained in the data set because, this data is taken, the image is taken from the same patient, and we're looking at the same part of the body, and it has the same disease. So we think that maybe we can use some way to actually exploit this shared information between different modality. So what we did is we have fused the middle layers of this encoder-decoder architecture so that this middle layer should correspond to what we think of as higher level concept of aorta. So all the information so we have the 2 different lower level layers for different image modality, but they share a higher level middle layers. So while training this architecture, what we do is we train the CT and MR pathway alternatively in each training iteration. So for example, when training the CT pathway, which you can see is red part, you will let the weights or parameters for the MR pathway to be fixed, and then train the CT pathway. And alternatively, in the next iteration, you will train the MR pathway, which is colored blue, while keeping the red part, which is the CT pathway, fixed. So this model has several advantages. So the first advantage is that it actually has accelerated training. So this is a plot of the validation accuracy of the fusion CT and MR model and the separately trained CT and MR model. So I don't know if you can see clearly, but on the graph, the accuracy for fusion models actually rise much faster than the accuracy for the separately trained models. And we also observe that there's slightly improved segmentation accuracy. So by accuracy, what I mean is we measure the global pixel-wise accuracy. That means we see if every pixel is classified correctly or not. And so the accuracy for CT modality is close. So for fusion CT model, we have 99.1%. But for separately trained model, we have 98.8%. And the accuracy for the MR model, actually, for fusion MR model is actually much higher than that for separately trained. So the accuracy for fusion MR model is 98.5%, which is 1.2% higher than that of a separately trained MR model. And we also observe some other very interesting behavior of this fusion model. So what we call is a learned shared representation. So what we do is, if we go back a few slides, so what we do is we put a CT image there, and so in the share layer, there will be some activations, which we call is feature maps. We take out that feature map for CT image, and we then put an MR image to the MR pathway, and there will be also some activation in the share layer, and we take out that feature map as well. And we compute the feature representation distance between these two feature maps. So what we use is a cosine distance, which is shown in the formula below. And you basically can think of each feature map as a vector, and then you can compute this distance relatively easily. And what we observed is that, so for the fusion model, so on the left, it's a separately trained. So what we did is we take out the image sequence of the same patient. The one is CT sequence, and another is MR sequence. So we compute the feature distance between each image in the CT sequence and each image in the MR sequence. And we plot this distance in the 2D matrix way in the heat map. So basically, you can see that the colder the color is, that means there's smaller distance. The hotter the distance, the hotter the color is, that means it's more increased distance. So for fusion model, what have we observed is that for CT image, that showing the aneurysm. So you can imagine the CT image, it starts from here and it ends here. So they're numbered from 1 to 72. And the CT image starts showing aneurysm around the image 52. So you can see it's the bottom part of the region. So the CT image actually shows a smaller distance from MR image showing the same aneurysm condition. So you can see that this relatively blue area is basically where the aneurysm looked at from the CT perspective is actually similar to the image looked at from the MR perspective. And but for healthy aorta looked at using CT image modality, actually has a much larger distance from the MR image showing what we call an aortic aneurysm. And also for CT and MR image showing healthy aorta, they only have smaller distance when they are looking at the same part of the body. That means if I took a CT image at this position and only the MR image at this position will show a smaller distance, so which is a small blue square at the left side. But this behavior only exhibits in the fusion models. That means this model are trained in the fusion by fusing their middle layers, but it's not exhibited in the separately trained models, which is shown on the left. And we also observe some other interesting behavior is that, so we have a pre-aligned CT and MR image pair. That means it's the same area of the aorta, and it's pre-aligned. That means we try to register them together into the close position. And if we then manually shift one of the image horizontally or vertically, it will actually increase the feature distance. And so for the fusion model, so on the right you can see it's a fusion model. In the middle is where there's no translation, so this very dark blue, that means the distance is small. But if you shift it, the distance will generally increase to hotter colors. But this is also, again, not exhibited in the separately trained model. And so the same effect also apply when we are manually rotating the pre-aligned images. So on above the blue line is for separately trained model, and below is the red line is for fusion trained model. That means if we manually rotate one of the image, the feature distance will increase. So we think that this behavior actually can be applied in future works to help us register the image in some way that can allow us to develop new methods to register maybe body areas that contain a lot of soft tissues. So in conclusion, we use the intermediate layer fusion to allow neural nets to make good use of the shared information between multimodality CT MR image dataset that cannot be closely co-registered. And so the fusion model train faster than the separately trained model and are more accurate and learn a shared representation of the aorta. And we also think that this could be potentially applied in the future to image registration researches. So this is the end of my presentation. Thank you.